look at us go. Back in the shed, and we have before us the transfer box. And one of the things I really enjoy about working with new and clean components is I get to wear my good clothes. Being such a fashionable kind of a character, I like to look my best even in the workshop. Now before we get into this, we have to have a discussion on bicycles. It's a poorly kept secret all of us Land Rover guys have them primarily as backup transport for when our vehicles are in the shed. We've got to get to work somehow. So this discussion is not so much aimed at us, but our beloved cousins who drive Nissans and Toyotas and may have forgotten some of the basic principles of gearing. Now on our way to work, we're quite often on the open road, or if we're lucky, going down a steep hill. And that will call for high range, which is a large cog driving a small cog. Pedaling is harder, but it enables our little bicycle to travel along the road at warp speed. Unless of course you live in Geraldton and you're going against the southerly, warp speed doesn't happen. However, if you live in Geraldton and you're going with a southerly, you've got to hang on. You'll be in Northampton in 15 minutes. Now sometimes on the way to work we encounter a steep hill, or we have the option of a shortcut through the quarry. That calls for low range. That is a small cog driving a large cog. Now travel speed is greatly reduced, but pedaling is much easier, and we have the torque necessary to overcome any obstacle that may hinder our progress. Memories of the past for some, realities of the present for others. So this myriad of gears is set up as you would see them in the box. Now the guy on this side here is the one that dangles out the back of the gearbox, called the output gear, and that one's going to spin at whatever gear ratio you've selected in the unit. In the middle is the intermediate gears, and it's a two cog system. We have a large cog, we have a small cog. The large cog is permanently splined into the output gears, and likewise will be spinning at whatever gear ratio the gearbox has selected. So the shaft on your far left here is the output shaft for your transfer box, and on that are two gears. We have the small one, which is high range, a large one, which is low range, and of the two, only one of them splined to the shaft and able to drive it. That is low range, seen here in the neutral position, hooked up to nothing. High range simply free spins, as you can see. So even though it's permanently splined in with these other gears, as we turn it, you can see nothing's happening. Your gearbox can be in whatever gear you want it to be, but power is going to stop right here and you're not going to go anywhere. Which is a good thing, because I recommend anybody playing with their transfer box gearing do so from a stationary position. Now low range has three settings and two ways that it can drive the shaft. Driven by our selector fork from the neutral position, position 1, we go backwards where it hooks in to a small cog that drives the large cog. And now, as you take your foot off the clutch, you are going to be in low range. We stop, and then using our selector fork, we drive forward into neutral position and then into high range, which is the second way this can drive the shaft. As it locks into those dog teeth, now high range no longer free spins, and it is able to drive the shaft in the high range ratio. Well, I don't think you needed to see any of that. It's quite obvious. My hair's grown back and it's colder. We were waiting on a part. It took 6 weeks to arrive, and the day it did was the day before we left on a big trip. So that slows the project down a little bit, which is a good thing because it's moving along at a blistering pace, like watching processionary caterpillars cross the road. You know, it can be all a blur. Anyway, we're going to take our brand new output shaft and we're going to put some oil on it. Then we're going to take our brand new high range gear and insert that on top with the dog teeth towards the rear of the shaft. Our brand new thrust washer, slot that on. And our old circlip, because that is going to be a temporary fix to check some end float. With our circlip in place, we can feel the gear is a little sloppy. The recommended end float is between 0.004 and 0.008 of an inch, and I reckon this is too much. Now if I grab my feeler gauges, set to 0.15 of an inch, which is nearly twice, and I pull that gear away from the shoulder or the spline on the shaft, I can fit it in there. It's a tight fit, but that's what it is. Almost twice over excessive the recommended end float. And in the book, it says that if that is the problem, then put on a new thrust washer and a circlip. But I do not believe these thrust washers come in incremental sizes. I think it's just one. So that's an issue. That's a problem that I might not be able to solve. So we have two choices. Either we live with the sloppy gear, which I don't think is a good idea, or we invent some kind of a shim. All right, I have an idea. I have here a piece of sheet metal. I think it's around 22 gauge, thereabouts. And I also have a second thrust washer. All right, we know our end float is 0.015 of an inch, and I'd like to add material up to around 0.01 of an inch to reduce that end float. Now that equates in sensible torque to 0.254 millimeters. Now our sheet metal measures in at roughly around 0.9 of a millimeter, making it 0.65-ish too thick. But I don't want to grind back the sheet metal because I'd like to keep some of its structural integrity. So that means we have to grind back our thrust washer. And this guy measures in at roughly around 3.147 millimeters, all right? And we want to take off around 0.656 millimeters, which is taking away what we need to add from the thickness of our shim that we're going to put in. And that leaves us having to grind this back down to 2.5 millimeters thick, and we should have it. But how are we going to do that? It's got to be a more efficient and less embarrassing way of doing this. I'll be with you in a sec. Our measurements are down to 2.55, which is still a little larger than our calculations called for, but not much. I think it's a good time to put it to the test. But before we do that, we have to create a shim. Nice smooth turn, it's good. Slightest bit of slop, and I think we might have gone a touch too far. As we slide in a tight fit, 0.007 of an inch does slot in there, but not the 8. So we're at the upper range of our tolerance, which is much better than where we were before. So it looks like our homemade shim has done the job. I can't guarantee it'll be a few hundred miles down the track before I know it's going to be able to withstand the pressures of being in the transfer box, but there you go. our caveman built shim. There's a few caveman tricks I could show you, but you'll be pleased to note that none of them involve the seduction of women. I just don't think the cudgel was ever an appropriate tool to be used in courtship, and I counsel anybody against its use. It's just a bad look. Hey, cricket. Well, with that obstacle out of the way, we can now set to the task that we came here for in the first place, which is reassemble the transfer box. Got some black tape there, that lets me know which is the front. I'm easily befuddled, and hopefully this will minimise the risk of me assembling it back to front. All right, the shaft. We've also taken off the high range gear for reasons we'll see soon enough. And the front of the shaft is the blunt bit, the rear has the threads. What we're going to do now is press on the rear bearing, not the front. We'll find that out soon enough. And the rear bearing is the largest of the two. So we have our greasy gears. High range lives on the front of the shaft with the flat face forward and the dog teeth facing the rear. Low range lives behind that, and they interconnect as such, and it has the selector groove facing the back of the shaft. Alright, so we'll take our gears, lock them together, grab our shaft from the rear, place the gears in their position inside the box, and feed through from the back. And we want to make sure we've splined low range onto the shaft and lower it carefully down. At this point we might want some rags just to protect our aluminium housing from damage. Now we're going to put on our thrust washer and shim and a brand new circlip. So now we have the rear outer race roughly in position. We're going to press on our front bearing. We have our case set up like such because I want the bottom of the shaft to be supported and not the lower bearing that's got to take the weight. So with this one, we've got it's held in place with a circlip. So we want to push it just below that spot. My intentions at this point is to put the case back into the press and push gently on the rear of the shaft and force that front bearing and race hard up against the circlip that retains it. Now we've got that all done, what we have is a nice smooth turn, but have a look at this back to front motion. All right, that needs to be eliminated. But another enormous problem is that since we pressed on our front bearing, high range gear has lost all of its end float and is fused to the shaft. That is a bad thing. I would think that if you engage low range in the vehicle with it like this, you'd almost effectively be in high and low at the same time, blow apart your transfer box, and if it didn't, and high range was able to turn, then there'd be rapid wear and a lot of heat and things wouldn't go well. I think I got to take this apart again. I got to do all this again and put on that original thrust washer. I think my shim technique, and I don't understand. The workshop manual says check the end float at the start. We did that, and we had the higher end of the clearance. Shit. We're back to where we left off with our original thrust washer. And now with our front bearing installed, all that extra end float that was on our high range gear has now been eaten up. In fact, the end float is now slightly below tolerance, but we do have a nice smooth turn, so I don't want to interfere with it. I think if it was super tight, we'd probably have to disassemble the whole thing again and run our original thrust washer over the grindstone and thin it out a little. But no. So what we have now is a slight bit of end float on the shaft that needs to be addressed. And then of course also some preload added as well, which we're going to do with the speedometer housing. If that further affects the turn of our high range gear and tightens it any more than it already is, then we'll have to go back to the drawing board. Although there is a procedure to take away the end float and to put on the appropriate preload, I want to try a little trick first. Okay, so having done the cheat method and just throwing the shims we had on and then tightening it all down, we can see that the shaft turns, but it's a little too tight, and it has gravely affected the turning of the high range gear. So we're going to have to go to the shop. We're going to need more shims. Alright, our shims have turned up. I've bought so much stuff from John Craddock. They've assigned me my own personal delivery truck all the way from the UK to America in 4 days. Unbelievable. Shims. So what I've done is I've put this into the press and just gently push the shaft backwards so that we've got our slop back. And now what we're going to do is we're going to get our speedometer housing, put that on without any shims, and we're going to tighten it down gradually and evenly until we have our desired preload on the bearings. Okay, what we have now is our slop is completely gone and the turn is smooth with a little bit of resistance to get it moving. All right, so we have 2 trains of thought depending on which book you're reading. The Haynes manual, which deals with series 2s to 3s, talks about wrapping a line around the low range gear and using a spring balance to get a pull weight of around 2 to 4 pounds to determine the preload. And the Green Bible kind of indicates that you just crimp it down and until your slop's gone and you turn smooth, which is where we are right now. I think I am happy with that. Anyway, so what we've got to do now is measure this gap, okay? And I don't have a way of doing it. I think the best option we have is to put together a selection of shims. The fewer, the better. And then jam them in at various locations and come up with a mean average of what thickness we think we need. Alright, well, straight off the bat, I just have these 2 thick shims that turned up, and if we look down the back here, they slot in not so bad, and up the top they don't fit in at all because obviously it's not quite as level as it needs to be. However, I would think that just these 2 here are a good place to start. So let's take this housing off, put these on and see what results we have. Alright, with our housing locked in place and our shims in position, we find that our preload has increased a little bit. Too much, I think. So it may benefit from a 3rd shim. A wispy wafer thin one, I think. Now, another thing we have to work on. So the end float on our high range gear, it's got a nice smooth turn, but it's slightly below the recommended minimum, which is 0.004, and ours is sitting on 0.003. However, I ain't gonna touch it. So this is all a delicate dance, as you can see. I'm sure you're going to get the gist of it. My next course of action will be take the housing off again, press the shaft slightly backwards to reset our slop, and then add on our wispy thin shim, tighten it all back down again, and see what results we have, and carry on as such until we are happy. Ooh, might have been wispy thin, but it made a difference. I think there's almost even the slightest hint of slop, so that's not good enough. So we know from our previous selection of shims, one was not enough and one was too much, so we're going to take some measurements. Our two chunky shims, they measure in at 2.03 millimeters. So now we put on our wispy thin shim and take the measurement of the three, and they measure in at 2.12 millimeters. Now we have a set of 4 carefully selected shims of various thicknesses, and these guys together measure in at 2.08 millimeters, which is close enough to halfway to me. We'll give them a try. With our third set of shims installed, I have to say I'm very happy about where we are now. We've got no slop, we've got a smooth turn and a modest amount of resistance as we do so. So from this point on, we have to take the housing off again. We have to press on our speedometer worm. Then we have to grease our shims to encourage the oil to stay in the box. And now we have to prepare our speedometer housing for the final fitment. Very exciting. Let's begin with our reconditioning. So what we have here are 3 little bolts, and what they do is they retain your speedometer cable into your doobie watch, so they should stay there. We're going to concentrate on these little screws that have got to come out. There we go. So under our cover plate we see the remains of what looks like a gasket. Alright, so keep that in mind. Put that somewhere where we won't lose it. And what we have in here is a seal. And then inside is a pinion within a sleeve. Now the sleeves are easily damaged, however they're not that expensive to replace. If you do want to give them if you do want to destroy them, just give them a hit with a screwdriver or a chisel, and that'll sort it out. If you don't, then grab yourself some multi-grips, get it so you can grab it, and then start twisting. And remember, 60 years of dedication. It's not going to start out that easy, but once you get the motion going, then you can add a pull to it. Keep your grip tight, and out she comes. Now, at the top of the pinion, if you look carefully, you'll find the missing bit from your speedometer cable. There it is. Yeah, you can put that on the shelf. Alright, what we'll do now is we're going to clean up the bits. We're going to replace the O-ring and the seal, and we're going to put it back together. So to start our reassembly, we can notice that the new sleeve lacks the groove where the O-ring goes, so we'll just bypass that step, I suppose, and stick it in. Alright, well, we're going to start off, I think we'll press in the doobie, what's that thingamajig, the top seal. Alright, let's get our former gasket. Just going to smear it around on the inside of the, where it's got to go. And up there, where the gasket is. Might smear some here where the sleeve's going to connect as well. Can't hurt. Leave those for a few minutes while it sort of does its thing. Oh, God, sticky stuff. Alrighty-o, let's press in that seal. If we can. Hopefully just with our fingers. There we go. Now, we'll give our pinion a liberal coating of oil. Oh yeah, I mean, look at that. And then we'll get some inside there with the seal. Plenty in there. And on the outside, let's not be shy at all. Lovely. Okay. Pinion goes inside. It's meant to. Press it up to that seal. Then when we lob it in the hole, we have to make sure that this chamfered section here is facing where the speedo worm will be. That's the idea. There we are. Looks good so far. We have a gasket. And we have our cover plate. And then our screws. So I think we remembered everything. Okay. The pinion spins. That's good. Alright, last thing we need to do now, I think, is install the seal. So we'll apply some goop, warm up the housing. Now it is a little beat up, okay? It is a little beat up. I could see this leaking, so we're going to stick a good wad of this muck in there as a line of defence. I think we're ready to put this together for real. Okay, this is the moment of truth. Okay, it looks like everything is held up. Everything is working. I'm happy. I am happy. Well, I think the knockoff bell might have sounded. It's gotten very dark and stormy out there, so I think it might be a good time to run away before the spooky spooks come and get me. Anyway, I'll see you in the next installment of the transfer box overhaul.